This is the solution for homework 1, A1, number 2. And this is similar to problem number 5 from the book, but there are a couple of small differences. In this problem, we're told that at an effective annual interest rate of I, 3 different payment options have the same present value. And the options are for part I, the present value of $3,250 at the end of 2n years. So we can represent that algebraically like this, 3250 v to the 2n, using the present value factor. Then number 2 tells us that the second payment option is the sum of the present values of 5,000 at the end of year t and 27,000 at the end of year 2t. So again, using the present value factor, we can represent this present value this way. And then finally, our third payment option is 2,080 immediately. So this gives us 2 different equations that we can work with. We know that 2,080 is equal to 3250 v to the 2n. And additionally, we know that 5,000 v to the t plus 27,000 v to the 2t is equal to 2,080. And we can work with both of these equations, but one thing that's sort of interesting about this problem, or one thing you need to be aware of in this problem, is at no point are we going to have enough information to solve for I, the interest rate, and thus we're never going to be able to figure out exactly what V is. Similarly, we do not have enough information to solve for N or T, which can be kind of frustrating in this problem, but it turns out we don't actually need to solve for any of those variables explicitly to be able to finish this problem. So to see how this is done, let's take a look at this first equation. If I divide both sides by 3250, I get v to the 2n, and actually let me write that as v to the n squared is equal to 2080 divided by 3250. That gives me 0.64, 0.64. And so if I take the square root of both sides, I get that v to the n is equal to 0.8. So notice we don't know what v is and we don't know what n is, but we do know that v raised to the n is 0.8. Okay, so we'll set that aside and we'll come back and use that in a moment. Coming down to the second equation, we see that this is basically a quadratic equation in the variable v to the t. Or in other words, what I'm saying is that I can rewrite this in the following way. 27,000 v to the t, quantity squared, plus 5,000 v to the t minus 2,080 equals 0. So now I can use the quadratic formula to solve for v to the t. And I'll let you go through and carry out the calculations there, but if you do this, you get v to the t equals 0.2. Okay, so how does that help us? Well, in this problem, what we are asked to do is calculate the present value of a payment of $11,000 at the end of year t plus n, using the same effective interest rate. So algebraically, we need to calculate this quantity, 11,000 v to the t plus n. Well, using laws of exponents, I can write that as 11,000 v to the t times v to the n, and fortunately I happen to know what v to the t is as well as v to the n. And so I can write this as 11,000. Let's see, v to the t is 0.2 and v to the n is 0.8. So if I multiply all this together, I get 1760. Okay, so like I was saying, we were able to solve this problem without actually ever figuring out what v, t, or n were.